Hello everyone, this is video 4, question 4 of the test 4 extra credit. So like the other 3 videos should be about this one. And woo, it's the final video I guess. So it says which one is a more stable comforter, and then I drew 3 of them. This is pretty dread. Like these are pretty close, but this is what they are. So wait first, and if you're wondering what its name, this would be its name, and then you could go to, I think, my second video, question 2, so you can see like the naming process. So what you need first to do is draw a chair. I'm really bad at drawing chairs, by the way, so this is like, so I'm just gonna give it my best shot, and I might just erase it a few times because I'm kind of a perfectionist. I'm not a perfectionist, but I think that's just, but I'm just gonna settle with that one. So the first we need to do is label our number atom. So, and then you get the first point difference. There's a bunch of different naming systems. Like you can start from here, then go around, and you can start here from going around. But I'm just gonna choose the most effective ones, like the most obvious ones, and then I'll explain why. They're false. Oops, I forgot to name this one. So what you first need to do is find first point or label write out where the shift roots are, 1, 2, 4, and then this one would be 1, 4, 6, and there's a bunch of different ones. I'll do one example one, but for these it's pretty obvious that they're not going to be it. So it'd be 1, 2, 3, 4, 5, 6, and then it'd be 1, 3, 4. So you need the first part difference, so you can count all these ones. First part difference and lowest, so it'd be the green numbering system. So number system, let me just erase all these in the mid side. Oops. It was this 1, 2, 3, 4, 5, 6, and then we can put that to our chair. So 1, 2, 3, 4, 5, 6, and then start filling out the chair. So 1 starts like this, and then it always goes up, down, and then does the angled. I think that's right. Yeah, that looks correct. So now we need to find out where all these atoms go onto this chair example. So this one's on the first one. So first, and then here's if it's a wedge, then it goes on the up, and if it's a dash, it goes on the down. So for this one, this is a wedge, and wedge means up, so it will go on this. Number 2, this is 2, it's a dash, so it will go on the down. And number 4, the fourth one's right here, so then it's it's a dash, so it'll go down. Boom. And then now we need to draw the chair flip, so let's draw a flip version. actually looks pretty good. Or maybe it doesn't. That's pretty good for a first try. So when you're drawing the flip version, in order for you to like number it, you see imagine this one like you are, this one goes on this side and this 4 goes on this side. So it'd be 1, or just remember that the 1, like for this version, the 1 goes in the upper right, and this version the 1 goes in the bottom right, and then you go around like again. And then that should work. That's how I remember it. If you remember a different way, then good for you. Right. And then I forgot to mention this, but all the angled bonds or the equatorial bonds are like the opposite. Like this is up and this is down, but they're angled down. So if there's an up version, then it'd be angled down, and if there was a straight down version, it would be angled up. If that makes sense. So you see how this is a straight up, so it'd be angled downwards. So they're always angled, they're just angled in the opposite direction of what the straight one is. Boom. And now we can put which one. So first one, it's a wedge, so that means it's up. First one would be right here. Second one, it's a down, so it'd be a down one, so it'd be right here. And then fourth one, it would be on a wedge, that's on the down one, so it'd be right here. And out of the chair flip, or the flip version and the original version, you can tell which one is the more stable version by seeing where the constituents are. So if it's on, constituents are on like the more, let me write up here because I'm gonna write in this area later. More equal, like more they are on the equilateral or the angled bonds, the more favored it is. So let's count it. And then there's also a important part. So since this, like this substituent is so large, like even if the other two, if this is on an angled or equilateral and the other two are on not, then it would still be, I don't know how to describe it, but it's like really important for this bond or this constituent to be on an equilateral because it kind of like outweighs the other two bonds. So even if like this bond was on a axial bond, which is a straight bond, and the other two will be on a equilateral bond, then it still wouldn't be that much stable if this is on the equilateral bond and these two are on the straight bond, because this is such a just like a large constituent. So it's important to keep that in mind. So this one has all three of them are on an axial bond, which makes it not that stable. You can tell because this is straight down, this is straight up, and this is straight down. Let me check if it's right. So the first one, axial up, second one, axial down. Yeah. So this one, oh, I should probably write this one better, but since this was on the down version, this goes over here. So I have one equilateral or two equilateral. No, all three of them are on the equilateral. I got confused because I thought this one was labeled this one, but it'd be right here, right here, and right here. So that's a really stable, or more stable than this one. So I'm just gonna circle this one. More stable version. And then start working on this one. So it'd be the same number system because all the constituents are on the same. on the same places, and then we start drawing a chair version. So this is 1, 2, 3, 4, 5, 6. So on the one it's on the up bond, I'm just gonna, I guess I can just redraw the entire chair. And then it's very useful to have this on your cheat sheet so you don't have to like remember how to draw it. So this one, it's a wedge, using the same logic we used here. This is on a wedge, so we'd be in the up on the first one. Second one, it's a wedge, so it'd be up. And the fourth one, it's on a dash, so it'd be down. And I draw the flip version. So this is 1 equilateral, 2 axial. And now we draw the flip version. That's wrong. Yeah, it looks really bad, but 1, 2, 3, 4, 5, 6. I'm just a bad chair drawer, so one, it'd be on the up one, so it'd be CH3 there. 2 be in the up one, so this is 2, so it'd be CH3, and this would be in the down one, so this would be CH3. See? I forgot 3 there. So out of these two, which one is more stable? This one has 1 equilateral, and has 2 equilateral. This one and this one. And this would have 1 axial. Even if this one turned out to be on not this one. This one turned out to be on a axial one. This one would still, the bottom one would probably still be more stable because this one is such a larger, this is what I was talking about earlier, but since this one is a larger constituent, you want this one to be on the equilateral instead of a smaller one in order for it to be more stable. So even if this one was on an axial, the bottom one's probably be more stable. So out of these two, which one is more stable? This one has 3 axial, this one only has 2 axial, so this one would be the answer. So the left one would be more stable. I think that's it. So thank you for watching my videos, and have a nice day.